All right, today we are cracking open a really fundamental idea. One that underpins, well, everything from ancient logic all the way to modern AI. We're talking about sets and mappings, which is kind of like the hidden code behind our reality. So let's just dive right in.
You know, everything has to start somewhere, right? Before we ever built machines that could think, before we even formalized the idea of numbers, we had to start with a concept so simple, so primal, that it underpins everything else. And that idea is just a collection.
And that's really the hero of our story today, the set. It's an idea that came way before any complex formulas, and it is the absolute bedrock of modern logic, and you guessed it, computer science.
Okay, let's make this real. I want you to picture a huge forest, just teeming with life. You've got trees, birds, rivers, all sorts of animals. Now, in your mind, I want you to just draw a mental circle around only the wolves. Isolate them from everything else. That act of selecting, that grouping, you just created a set. See? It's that intuitive.
The real key here, the magic phrase, is well-defined. In math, clarity is everything. For something to be a proper set, there can be absolutely no gray area, no ambiguity. An object is either in the set or it is out. It's that simple. A wolf belongs to our set of wolves. A tree does not. It's a clean binary truth.
So once we get this idea of grouping things, the next logical question is, well, how big can these groups get? And this is where we start to explore the pretty mind-bending boundaries between the things we can count and, well, the things that are endless.
So on one hand, we've got finite sets. These are just collections with a limited, countable number of things in them. A perfect example is the days in a week. There are exactly 7, you can list them all, and then the list just ends. But on the other hand, you have infinite sets. Think about all the natural numbers. You can start counting 1, 2, 3, and you could literally keep going for your entire life, for all of eternity, and you would never ever reach the end.
Now, because these ideas are so incredibly powerful, mathematics has basically created its own universe of predefined go-to sets that get used all over the place. Let's take a quick look at how they create a framework for all the numbers that we use.
This table lays it all out pretty nicely. We start with n, the natural numbers, the ones we count with. Then we expand out to z, the integers, which brings in the negatives and 0. Q gives us all our fractions, the rational numbers. R includes, well, basically everything on the number line, even weird stuff like pi. Those are the real numbers. And then finally, C brings in the complex numbers. The point is, every number has a home, a set where it belongs.
So to talk about whether a number is at home in a certain set, we need a language. And really, that's all mathematical notation is. It's just a super efficient shorthand for describing relationships, like the simple act of belonging.
All right, let's see this in action. Say we have a set. We'll call it M, and it only has the numbers 1, 2, and 3 inside. Now, let's take the number 2. We just asked the question, is 2 an element of M? Well, yeah, of course it is. And we write that with this little symbol, which just means is an element of.
And of course, the opposite is just as important. Using that same set M, what about the number 5? Is it in our little collection? Nope, it's not. And for that, we use the exact same symbol, but with a little slash through it. It's a simple symbol that tells a complete and absolute truth. No ambiguity.
Okay, so we have these collections, these worlds of objects. But if you think about it, on their own, they're just static containers. They're kind of silent. To really bring them to life, we need to build bridges between them. We need to forge a connection.
What if we could create a rule that actually lets one set communicate with another? What if an element in one collection could point directly, specifically, to an element in a completely different collection? And the answer to that is a mapping, which you probably know it as a function. It's nothing fancy. It's just a precise rule. It takes every single element from your starting set and connects it, or maps it, to exactly one element in your destination set. It's really the engine that creates relationships.
So check out how this works. On the left, we've got set A, with a cloud, a star, and a square. On the right, set B, with an oval, a triangle, and a circle. A mapping is just the rule that connects them. The rule could be anything, really, but here it connects the cloud to the oval, the star to the triangle, and the square to the circle. The important part is that every single thing in set A is precisely connected to exactly one thing in set B. Every input has one and only one output.
And this is where it all comes together. This isn't just some abstract math class concept. This simple idea, a collection, and a rule connecting it to another one is, and I am not exaggerating, how our modern digital world is built.
Think about it. An AI model is just a very, very complicated mapping. It takes a set of input data, like all the pixels in an image, and it maps it to an output set, maybe with labels like cat or dog. A financial trading system, it maps a set of market signals to a set of actions, buy or sell. The social media feed on your phone maps the massive set of all possible posts to that specific little set that you actually see. It is everywhere.
This right here, this is the fundamental logic loop of all computation. You have a set of inputs, you apply a mapping, a function, a model, whatever you want to call it, and you get an output, a result, a prediction, a decision. This is basically how machines think.
And that's the core takeaway. Every single time your phone recognizes your face or a trading algorithm makes a split-second move, it is performing this fundamental dance between sets and mappings. This is the architectural blueprint for artificial intelligence. So, just to recap the three huge ideas we covered, a set is just a well-defined collection. An element is any single object inside that collection. And a mapping, that's the powerful rule that connects one collection to another. That's it.
So in the end, whether you're isolating wolves in a forest or you're building an AI that can navigate a whole universe of data, the foundational story is exactly the same. It all starts with a simple, elegant, and unbelievably powerful idea of the set. So, what will you build with it?